I want to talk about capacitive amplifiers and talking about capacitive amplifiers in sort of with a high gain voltage amplifier, maybe like an op-amp type structure, where the capacitors are sort of setting the dominant behavior in the feedback, and then asking the question, what happens when I put, say, a resistive element in a certain place? Depending on where you put them, you get different effects. And I want to kind of show you an interesting case where you might think at first, in a very high gain situation, I wouldn't have to worry about it. Or maybe I could reduce it, or maybe it'll just, there's some very simple things, but it's really important to kind of see that the gain actually will affect things in a way that you may or may not have initially predicted. So what you start off with is you have an input, double capacitors, and a resistor here with a voltage source at this point. Now imagine if just to kind of get a thought process, if the R was infinite, so in other words there's no connection. So you might imagine that looks a lot like this op-amp circuit underneath here, where I have a charge there and I need to deal with the charge. Again, charge can be set in all sorts of ways. I can certainly write my equations out from V in with V1 in the middle and V out. I know also V out is related to V1 because I've set that in terms of the gain of that amplifier, which is this voltage controlled voltage source. Okay. So then I can start doing things and grouping terms together. And one of the things I notice is I have all the S's here, and I don't want to necessarily divide by S initially, but I notice I get C2 and then I get capacitance divided by the gain, which of course, assuming S is not equal to 0, I get this nice response, which is basically just a gain factor for all frequencies. So basically this is not a differential equation. Representation. It just means that if S is equal to 0, which means that there is a offset in the output. Okay, so I get some offset in the output. But the issue here is that, well, this gain is fairly large, particularly compared to C1 plus C2 over C2, compared to C2, then I can kind of ignore this term. And this gain just becomes a minus C1 over C2. But then I have to have the offset, which is what the S equals 0 implies. And there's many different ways to get to this kind of a question, but basically one way or another, it basically means there's an offset missing. You have to kind of put the offset in. And so in this case, this will be set by, say, the charge at the node. In this case, it would be a charge at this node if there was no resistance. You don't know what it would be, but you could also set it, so that's also a positive thing. I could also have gotten to this result by just looking at the simple differential equation for C1 and C2. That's another way to solve it. All would work just fine. And then I could imagine C1 over C2, the gain is minus 2 because of the numbers that are put there. So as a result, everything is pretty straightforward there. So not surprising. You've probably seen structures like this. You've also probably seen that the overall capacitance effect here is pretty small when you have a reasonably high gain. But in other words, if the feedback gain here is pretty least or relatively low gain, then as long as the gain of the amplifier is significantly higher than that, or the gain, in that case the op-amp, the gain of the voltage control current source is higher than that, I basically can just say, yeah, it's just not relevant. Great, so let's imagine now I have a resistor that's not infinite, but let's say it's like 1 megohm, fairly moderate value to work with. Well, I add that term into the equation here, and then I again continue grinding through. Well, again, I can get to this stage. You can start to see how we're starting to group things over the A sub V. And then a little bit more gives me V out over V in is minus C1 over C2, like what we had before. But interesting, and I also get a 1 plus a C1, C2 over C2 A sub V. Again, a term we would know is be negligible. Again, the gain is 2, so I'm not going to worry about it. But even if like the gain was like 100, or this sort of open loop gain of 100,000 or of 10,000 of this voltage controlled voltage source, or the gain of this amplifier, it's going to be pretty small. But notice something else changes here that isn't quite what you might have initially thought. This R actually has an A sub V over it. So the term I'm going to get here is an R times A sub V effectively, which means that my resistance looks like it went up by the size of the amplifier gain. So that means it's A sub V over R and A sub V over R here. Now that's an interesting question. And so that's what kind of starts to show up into my time constant. Well, okay, let's assume that's negligible. This reduces down to C1 over C2, again, small number, but then I get all of these terms. Well, this looks like my time constant. And you're like, okay, great. So I'd get a normal response like I would have expected anywhere else. Look, I get a nice high-pass response, right? I'm going to get a high-pass response out of this, given that you can see the sort of C and R in the front end. You're not shocked at a high pass. But look at what the value is. It's that R times C2 times the amplifier gain. And you think, wow, that will really increase that effective time constant. And so now I got a time constant like around 10 milliseconds, where if it wasn't for that, it'd been like 1 microsecond. And so that definitely shifts it, and you can definitely see there's an effect here of where you end up putting this resistor in this place, and it gets almost in some sense multiplied up, giving you a much larger time constant, which in fact you might want without having to then make your resistor quite as large, because that sometimes a large resistor is costly. So these are different techniques that can work, and it's an interesting problem to kind of get a sense of what your opportunities may or may not be.